Good morning, 3U chemistry students. Today's lesson is going to review a bit of our last day's lesson and then move forward. So in the last lesson, you learned independently about 3 gas laws that have been developed based on observations of how we see gases behave. So the first law is looking at the relationship between pressure and volume. And if you put a lot of pressure on a gas, you can make its volume much smaller, so you can compress it. So that's how we get like a lot of propane gas into your barbecue tank, for example. And that law credit is given to a scientist by the name of Boyle. So we call it Boyles Law. And here's the formula. The second law is looking at the relationship between temperature and volume of a gas. And if you heat up a gas sample, the molecules move much faster, therefore they're kind of bumping off each other more frequently and harder, and that spreads them out, so the volume gets bigger. So that is Charles' law. And then finally, we have a relationship between pressure and temperature, and that is Gay-Lussac's law, which I sometimes just shorten to GL. So this is saying that if you have higher pressure on a gas, it can increase the temperature, or vice versa. If you increase the temperature, you can increase the pressure. And it's sort of a similar reason. If you increase the temperature, the molecules move much faster. Therefore, they hit off the walls of the container more frequently and harder, and that puts more pressure on the inside of the walls of the container. So Boyle's law is an inverse relationship because if pressure is great, volume of gas will be small. Both Charles and Gay-Lussac are direct relationships. A high temperature gives a big volume, or a high temperature gives more pressure. Okay. So there's one thing you need to remember if you're using Charles and Gay-Lussac's formula, and that was the temperature had to be in Kelvin. You couldn't use degrees Celsius because of the fact that there's negative values, and that would just mess up the calculation. So we use the Kelvin scale, and it's easy to convert. You just add 273 to any temperature in Celsius, and that will be your Kelvin temperature. The other thing that's important is there's lots of ways to measure pressure, such as millimeters of mercury, atmospheres, kilopascals, PSIs, if you're talking about tire pressure, pounds per square inch, torrs, there's even more. It really doesn't matter which one you use, these formulas will work. However, you must not have a combination of 2 units. I think I said formulas there. Which unit you use, but you must use matching units. So if you're given 2 pressures that are in different units, you have to convert one to match the other. And you can use a conversion factor based on this. Okay, so today we're going to look at combining all these formulas together so that we could talk about a situation where you're changing 2 things at once and not keeping the other variable constant. So you can have a change in pressure and volume and see what the effective temperature would be, for example. So it's called the combined gas law, which for obvious reasons. And to set it up, I'm just going to put down Boyle's law. Whoops, except we're not going to start with P2. P1 V1 is equal to P2 V2. So there's Boyle's. And then if I were to add Charles into it, V1 over T1, I'd put T1 there and T2 here. So you can see that we have Boyle's initially, and then V1 over T1 equals V2 over T2. There's Charles. And then we have P1 over T1 is P2 over T2, which is Gay-Lussac. So basically we've just combined all the formulas. Now, in so doing, this gets a little more complicated when you want to isolate the one thing you're solving for. So I thought we'd just go through a couple of examples of how you would do that. So if you were asked a question where you wanted to solve for P1, the initial pressure of a gas. So it told you the other 5 quantities wants initial pressure. Then what you need to remember is to get something by itself, you have to get rid of the other things. And to get rid of other things, you need to do basically the opposite operation to them. And then you're going to want to do it to both sides of your equation. So we want P1 all by itself. So currently P1 is being multiplied by V1. Well, how would we get rid of that? We would divide by V1. That would make it go away. But you can't just do that on one side of an equation. You need to do it on the other side too. So whatever we do to this side, we're going to do to this side. Okay. Currently P1 is being divided by T1. So if we were to multiply by T1, they'd be able to cancel. But of course, better do it to this side if you do it to that side. So this is how we get rid of everything. This is what we are left with. So that is the final formula. Okay, we could do another example. Let's solve for, we could do 6 examples technically, but I don't think we need to do that many. Supposing we're asked to solve for a temperature. T is on the bottom, so I'm going to say T2, okay? When something's on the bottom, it's a little harder to figure out how to get rid of it. So what I would do right away is flip the equation upside down. As long as you do it to both sides, you can do whatever you want. So the other thing is I like to have my thing on the left that I'm solving for. So I'm going to flip it upside down. Okay. So I'm going to put T2 on the left too, just so I can solve for it. And I'm going to put it on top because I'm making the whole equation upside down. Like that. So I've just rewritten what we have up here for the combined gas law backwards and upside down. Okay. And then we want T2 all by itself. Currently T2 is being divided by P2 and V2. So I would need to multiply by both of those to get rid of them, which means I have to do that to this side as well. And then I can cancel. So tidy it up. T1, P2, V2, all over P1, V1. Okay, that's the hardest part, is just getting the formula you need. And then you're kind of plugging in the numbers and making sure things match. So to keep yourself organized and know, well, what was the initial, what was the final, because that will mess you up for sure. Make a list when you start a question and designate, the 1 and 2 after everything. So the example we're going to do says I have an unknown volume of gas at a pressure of 50.6 kilopascals and a temperature of 325 Kelvin. Oh, this question is too easy. It's already in Kelvin for you. Then it says, if I raise the pressure to 1.2 atmospheres, decrease the temperature to 320 Kelvin, and measure the final volume to be 48 liters, what was the initial volume? So the question is initial volume. So that is V1 is the question. Okay. It doesn't matter if you write that first or where you write it. So 50.6 and 325 Kelvin are initial conditions. So P1 is 50.6 kilopascals and T1 is 325 Kelvin. Then I'm raising the pressure. So P2, notice pressure is not in matching units at the moment, so we will need to deal with that. The temperature, when I'm finished, I'm going to cool it off a bit, so it's only going to be 320 Kelvin. And then the final volume, V2, is 48 liters. Okay, so the first thing you would always check is, if I'm in Celsius, I need to add 273 to those temperatures. But this question was nice to you and already has it in Kelvin, but beware of that. Now, here's the other problem. These have to match, and it really doesn't matter which way you go when you decide to make those match. You either have to have them both in atmospheres or both in kilopascals. So I'm just going to switch the first one. So at the top, I gave you a relationship, so it's a conversion factor. So I want to get rid of kilopascals, and I'm going to put it into atmospheres. So the conversion factor says 1 atmosphere is the same as 101.3 kilopascals. So kilopascals is going to cancel, and I'm going to have 0.500 atmospheres. Notice I kept 3 significant digits because my original pressure had 3 significant digits. Okay, now I'm solving for V1. So I'm just going to scroll this down a little bit so we can look at the formula again. So V1 is on the top, so we don't need to put it upside down. We'll just do the whole formula here. So P1 V1 over T1 equals P2 V2 over T2. I want V1 by itself. So to get rid of P1, I'm going to divide it out of both sides. Notice the other side won't change. Like, you're still going to have the exact same stuff. You're just going to add things to it. So I'm going to divide out P1 out of both sides, and I'm going to multiply both sides by T1. So that is my correct formula. And now I'm going to find out what was that initial volume. So P2, 1.2 atmospheres, multiplied by V2, 48 liters, times the initial temperature, 325 Kelvin, and I'm going to divide by T2, 320 Kelvin, multiplied by P1, which we said we needed to use 0.5 atmospheres. There. Okay. Now, by doing the units, you'll see that Kelvin is going to disappear, atmospheres is going to disappear, and you're going to be left with liters, which makes perfect sense because we are solving for a volume. So, on your calculator, a little hint. Take 1.2, multiply by 48, multiply by 325. Then push equals. Then say divide by 320. Push equals, say divide by 0.5. If you don't use some equals in there, your calculator will get confused. Okay, so it comes out to 117 liters. However, if we look, we have some data that had 2 significant digits. So you really should be changing that into scientific notation. So it's going to be 1.1 maybe, but then you look at the 7, that becomes 1.2. You move the decimal places 2 places. So essentially 120 liters. Okay, that is it for today. I think there's 3 more questions for you to practice with the combined gas law. And if you can rearrange those formulas, you should be finding Charles and Gay-Lussac and Boyles much easier to rearrange. And please check your answers at the bottom.